So last week we introduced the complex number representation of the polarization state. For polarization state described by this E vector A exponential for plane wave, plane electromagnetic wave with some polarization, we can describe the E vector as the real part of this complex vector. Here A is a complex vector with its two components be complex separately. Both AX exponential I delta x and AY exponential I delta y are complex variables in general. So if we do not care about this part describes the phase variation along the propagation direction. If we do not care about this part, we only care about this complex vector A, then this complex vector A gives us the information of so-called polarization of this wave. This vector describes the polarization this complex vector gives us the information of the polarization of this EM wave. So to discuss how to express the polarization, we have at least three different ways. The first way is to write down the A vector directly. This is the way to express the polarization of the EM wave. The second method, we use the so-called chi. The chi is defined as the y component of the A vector divided by the x component of the A vector. Okay. So this representation can be written as AY over AX times exponential I delta, where delta is equal to delta Y minus delta X. Okay. So once we know that this chi, we can write down the A. Only one thing uncertain. Okay? We do not know the exact value of AX exponential I delta X, but we know the ratio between the Y component and the X component of the A vector. Okay? We can write this as A can be written as AX exponential I delta X times, say, X plus chi Y. Okay? So once we know chi, we can write down this vector. We can write down this vector. However, we don't know this part. So this part is not important in determining the polarization state of the waves, because what does delta x mean, we can easily to change the value of delta x. How? If I change our coordinate from x to x prime is x minus x0, say, okay? Then, if I write this as, here we have, 我把它换成 c 嘛。Here we choose the propagation direction to be along the z-axis. Then, if I change the coordinate system, the origin of the coordinate system from z to z0, then we can define a new variable. Here we encounter exponential minus I k z can be written as exponential minus I k z prime plus z naught. Okay, then we can factor out exponential minus I k z naught, exponential minus I k z prime. Okay. Then we use z prime to replace z. Then this factor will be multiplied to 8. Okay. So you can just treat delta x as something like this. Okay. You can change your coordinate origin, so you can change the value of delta x. Okay, so delta x is not important in representing the polarization state. You can also change the time coordinate, which means that we can count the time, and we can start our counting of time from different point. Okay, say for example, I change t to t prime equal to t minus t dot. Okay, then we can have an additional phase factor from this exponential I omega theta. Okay, 就是说这边我可以任意去改变这个 delta x， 我只要坐标改了，或者是我码表计时的开始点不同。这个 phase 其实都会变，所以这个东西它不是 polarization 的部分，就是 polarization 里面这个 arbitrary phase 不重要。就是我们在讲一个光的所谓 polarization state 的时候，不需要特别去强调这部分啊。就这部分的话有一个 ambiguity 啊，就是它不是一个决定性的东西啊，所以这个东西我可以任意改变它，没有问题。我只要改时间的起始点或改坐标原点的位置的话，都是同样一个 polarization state. So we can change this phase factor by changing coordinate axis, or change the clock starting point. Then I can change this phase factor. On the other hand, I can also change this amplitude AX, because according to the fact that photon is a kind of boson, we know that boson has the property that we can have many boson in one quantum state. OK， 就一个量子状态里面可以有很多的 boson， 没有问题，它不满足所谓的那个叫做exclusion principle 啊。exclude 就是那个 exclusion principle 是适用在 fermion， 而不是适用在 boson。OK， 那 boson 可以在很多个 boson 可以处于一个共同的量子态。啊， 这是没问题。那波种数量变多的时候，就相当于是 amplitude 变大，好，这 amplitude 就是说 we can put many boson to one single quantum state. The result is just to change the total amplitude. Okay. So this part is also not important. Okay. So that's why we can use chi to represent the polarization state without knowing the exact value of AX and delta X. Okay? There is another approach that we can represent the polarization state of the electric field. We use the so-called Jones vector. Jones vector. Jones vector representation. Jones vector representation is nothing but just write the two components AX exponential I delta X and AY exponential I delta Y as the two components of the 2x1 column vector. This is the so-called Jones vector representation of the polarization state. However, just as I emphasized that the absolute amplitude and the absolute phase is not very important. Okay, so we can normalize this vector. We can normalize this vector to keep its length equal to 1. It is enough to represent the polarization state. Okay. 就是说你可以把它归化变成长度是1的向量，就足以去表达它是一个什么样的 polarization state 但你不 normalize 它可不可以？也可以啦就是说其实两种表达方式都可以。So if I normalize this J vector, then we can rewrite J as the form cosine psi exponential I delta sine psi. Okay, I can explain what cosine psi, sine psi, and this is we can factor out the absolute value of the ax squared plus ay squared. Okay, and then this can be I can also factor out exponential I delta x. Okay, and then we have this ax over square root this and ay over the square root this times exponential I delta. Okay, we can factor out this factor, and then we can ignore. We can just jump this factor to obtain this expression. Okay, that's because the sum of this square plus this square is equal to 1, just like cosine square plus sine square equal to 1. Cosine square plus sine square equal to 1. Okay, so we can define this as cosine psi, and we can define this as sine psi. Okay, and we already know that difference between delta y and delta x is defined as delta. So here we have an additional phase factor exponential I delta. So I can write this as cosine psi exponential I delta times sine psi. Okay. This kind of representation is called Jones vector representation. In this normalized form, we know that the amplitude AX is not important. Or we can say that the amplitude, this part is not important. Okay? And this phase I have already explained. We can change our coordinate system so that this delta x can be included in the phase vector about the propagation in space and time. So only the difference delta y minus delta x is important in determining the polarization state of this light. OK， 好，这个是关于所谓的 Jones vector representation 啊。那接下来有一个很关键的东西，就是说，因为这是复数向量嘛，复数向量的话呢，我们在表达复数向量的内积的时候要很小心啊，它跟这个实数向量有一点不一样啊。So in general, this Jones vector is a complex vector. We can define the scalar product of two Jones vectors or scalar product of two polarization states. Okay. By doing that, before doing that, I must emphasize that for complex vectors, the definition of scalar product is a little bit different from the real vector scalar product. Okay. We have already learned one specific example, say the right-hand circularly polarized light. Right-hand circularly polarized light can be described by AX equal to AY. Okay, and if I denote it as A, and delta is equal to minus half pi. Minus half pi. So if I write down, if I write down the Jones vector for the right-hand circularly polarized light, the normalized form is given as this. Okay, because when AX is equal to AY, you see that cosine psi is equal to 1 over square root 2, and the sine psi is also equal to 1 over square root 2. Okay, and the exponential I delta is equal to exponential minus I half pi, which is nothing but minus pi. Minus. So this is the right-hand circularly polarized light, the polarization state. You see that the right-hand circularly polarized light has the form that its x component is real and its y component is pure imaginary. So how about we define this? Can we define the, if we follow the original rule of real vector to define the scalar product, then we will get into trouble. Because, for example, if you calculate J delta J, okay, we know that for a vector, the vector square is defined as the vector scalar product with itself. Okay, So if we use this definition, then we encounter this and we get 0. This is nonsense, okay? Because we know right-hand circularly polarized light is not a 0 vector. Okay? This is not a 0 vector. So how to modify the definition of scalar product so that we will get a reasonable result? The modification, the correction is that we should define J stop of J of the scalar product of J vector, scalar product between J vector and itself. Okay, this is the correct definition of scalar product. This is equal to this. You see, the length or magnitude of the J vector now is equal to 1 because the scalar product of itself to itself is equal to 1. Okay. So in this way, we know that we already know right-hand circularly polarized light can be represented by this J vector. I write this as JR. JR is equal to this. And how about JL? JL means left-hand circularly polarized light. Left-hand circularly polarized light can be represented as 1 over square root 2, 1 times I. Okay. So if I want to know the scalar product between JL and JR, if I want to know the scalar product between JL and JR, I can write it as JL star dot JR. Okay, so this is equal to 1/2 1 times 1 plus I times I give us 0. Okay, this is reasonable because the right-hand circularly polarized light and the left-hand circularly polarized light are not only two independent polarization, but they are orthogonal polarization. Orthogonal means it is a generalization of the concept of perpendicular 就是说我们现在如果说两个向量垂直数学上的说法是说它叫 orthogonal 正交那正交对于这个实数向量怎么定义很清楚，然后呢我们肉眼看得到的也觉得很清楚就是它就是夹直角。可是对于复数向量，什么叫做正交呢？就需要更小心去定义那我们把右旋跟左旋定义成正交，听起来蛮合理的，对不对？因为右旋里面完全没有左旋的成分，左旋里面没有右旋的成分，就是这个，就好像这边说，我两个正交向量是什么呢？这个向量要投影在这个向量上，结果投影是0，那右旋要投影在左旋上面就没有这个成分所以这个很合理So this we can also write this as JL dagger times JR. Dagger means this. Transpose and complex conjugate. Transpose, we change the column vector to a raw vector, and then take the complex conjugation. Complex conjugation. 这边写错了，这是负 I 负 I 乘以负 I， 但一样是零啊。JL dagger times JR. Okay, then the result is 1/2 1 minus 1 equal to 0. This notation dagger, this notation dagger means Hermitian conjugate. Hermitian conjugate means transpose and complex conjugate. 好，就是把它转至并且复共轭啊，转至并复共轭啊，这整个合在一起，这个动作就是叫做 Hermitian conjugate， 叫二米共轭啊。那二米共轭的数学符号是一个小匕首啊，一把小的剑叫 dagger 啊，就是写在这个上面啊。所以当我写 dagger 的时候，我这边我不写箭头，表达的是说，我用这个矩阵的语言去描述它啊。那当我用箭头的时候，表达的是说，我用向量的语言去描述它啊。比如说这个的话，我可能具体怎么写比较好呢？这个具体写法会变成这样。I can write JR vector as 1 over square root 2 x minus I 1. Here, x hat, y hat are the two unit vector along the x axis and the y axis. And JL is 1 over square root 2 x plus I y hat. Okay, then so JL star or the JR is 1/2 x dot x give us 1, x dot y give us 0, y dot x give us 0, and the y dot y give us 1, and the minus I times I is 1. Okay, so this is equal to sorry. OK， 我知道了。这边就要变成 sorry. Here I take the complex conjugate. So here. Zero. Okay. If you use the matrix representation, then you write this as JL dagger times JR. Here, JL dagger is a raw matrix, and JR is a column matrix. And you also get the result 0. OK， 这个是关于这个正交性的这个表达。So I can write some example for you. X polarization can be written as 1, 0. Y polarization can be written as 0, 1. And right hand separately polarized light. Usually I write this as R hat is equal to 1 over square root 2, 1 minus I, okay, you see that I can write this as so this is just okay, and the left hand circular polarized light is written as this. So you see that you can check the result. This is using the vector notation. If you use the matrix notation, you can write the result as R delta L equal to 0. Okay. You have to be a little bit careful to know that in some other textbook, you may encounter the situation that the author represents the right-hand circular polarized light as one positive I, and left-hand circular polarized light as one negative I. That's because if you adopt the convention that if you describe the propagation of the wave having the phase vector written like this, here you have positive coefficient for space and negative coefficient for time, then you will have this convention, this positive I, negative I. However, in this textbook, we adopt this convention. Positive coefficient for time and negative coefficient for space, then we get this minus I, positive I. OK， 好，那其实都只是一个 convention 啊，就看你所用的 convention 不一样，你的那个表达方式就跟着改变啊。这个没有谁一定对或一定错啊，就只是一个用刀叉，一个用筷子，就这样而已啊，没有什么了不起啊。那 physics is the same, only convention different. OK， 这就好像那个你们如果知道说，比如说研究那个跟相对论有关问题的人啊，他们分成两组人啊，一组人呢，比如说是高能物理的人呢，你会看到他们写一种东西叫做那如果是研究重力的人呢，他们就比较习惯写这个叫 metric 啊。那谁正谁负啊？其实真的不一定，这个只是一个定义而已啊，就是看你希望怎么表达啊。So when we say something about relativity, those guys major in high energy physics, research areas about high energy physics. You will encounter this kind of representation about the so-called metric tensor. Okay, then for those guys study research about gravity you may encounter, they use this matrix to represent so-called metric tensor. Okay. So which one is positive, which one is negative, is dependent on the convention, okay, not different physics, okay? Just different convention. 好，然后呢，那我们一旦有了这一些表达方式之后啊，你可以看到就是说 ，so once we have these notations, you see that we can represent the right hand and the left hand circularly polarized light coalition as the superposition of the X and the Y coalition. Okay, you can use X and the Y polarization as the basis vectors and use them to write down all kinds of polarization. Okay. However, you can also use right-hand circular polarization and the left-hand circular polarization. We can use right-hand and left-hand circular polarization and use them as the basis vectors, and their superposition gives us all kinds of polarization. For example, the X polarization. An X polarization can be understood as you have a component rotated counterclockwise. You can have another component rotate clockwise. Then you sum them over. Then you get the polarization vibrate along the X direction. However, if you take the difference of them, you find the vibration along the Y direction, just like this. 比如说，你可以用右旋光、左旋光去叠加出 X 偏振，也可以用这两个去叠加出 Y 偏振。好，那当然也可以反过来用 XY 偏振去叠出右旋跟左旋。好，所以这个都没有一定啊，就是反正就可以用两个独立的去叠出别的。好。 然后另外呢，就是说我这边稍微提一下，就是说这里我们所遇到的 Jones vector 的这些数学呢，其实说穿了跟处理电子次旋的数学是一样的。好 ，So now we encounter some mathematical formula to describe the polarization state of light. You can see that these mathematics tools are almost the same as scientists used in studying or representing the electron spin state. Electron spin. For electron spin, if I write the column vector like this, 1, 0, this represents spin up, and this represents spin down. Okay, so that's why in quantum computing or quantum information, we can encode information in electron spin and or encode the information in photon polarization. OK， 好，那事实上你也可以说，我也可以把这个资讯编码在光子的自旋上。啊，确实，右旋左旋这个东西的确会直接跟光子的自旋有关。好，那所以这边来讲的话，相当于说偏振可以用自旋去叠加出来，对光子来讲，好，对光子。好，那我们再看几个简单的例子啊，看看这个Jones vector 表达的polarization state。So now we see that this is the X polarization. We can write its Jones vector as 1, 0. So this is Y polarization, its Jones vector is 0, 1. Okay? And how about this 45 degree? Okay? It is 1 over square root 2, 1, 1. And negative 45 degree. This 1 minus 1. Okay? And we have already written the right hand and left hand circular quadrant. Let me try to write down a simple elliptic polarization state. This one. Suppose now we have suppose we have an ellipse whose semi-major axis A to the semi-minor axis B is equal to 2 over 1. Okay? And its orientation angle phi is equal to half pi. Then you see that this is nothing but AX equal to AX to AY is equal to 1 to 2. Okay? So this can be written as this. Here, if I have minus I, then it revolves counterclockwise. Here we have positive I, which means it revolves clockwise. Okay? So this is the polarization state to represent this elliptical polarization. 好，那剩下的这些大家就自己看一看啊，应该没有什么太大的问题啊。那我们边勾几题习题。So homework.这里面几乎我好像全部都推导过啊，所以这个你大概不用费什么功夫。So now let me move to chapter 4. 第4章应该是这学期的课里面最重要的一章啊，所以这边请大家务必多花一点功夫去了解它。Chapter 4, Electromagnetic Propagation. So up to now, we talked only about isotropic medium. Isotropic means there is no difference in different directions. Okay, so if you apply electric field to the medium along, say, x direction, you polarize this medium, and if you now apply electric field along the y direction, you can polarize this medium as easy as you polarize the medium along the x direction. There is no difference. So if the medium has this simple property, then we call it isotropic medium. Isotropic means no difference in different direction. Okay. Now we discuss the new situation, anisotropic medium. Anisotropic means there is indeed a difference between different directions if we apply the electric field to the medium. For some direction, it is easier to polarize this medium, and along some other direction, it's more difficult to polarize it. 就是你可以把它看成说这个介质，你要加电场去极化它的时候，一个方向上比较容易，另外一个方向比较难。就是它的那个polarization 的难易程度不一样。那这就会造成这个光在里面传播行为会有一些比较不同的地方。这是我们第4章需要去讨论的。Specific example for isotropic medium can be air, water, glass, something like that. 就你这个水啊、空气啊、玻璃啊，都是 isotropic， 跟方向没有关系。但是呢，如果是 crystal， 那就不一样Usually, crystal has the property that they have some anisotropic property. Okay. So, say for example, calcite 方解石方解石就是其中一个例子So, if we want to describe the anisotropic property, anisotropic electromagnetic behavior of this medium, then how can we do? Okay, we already know that there for linear medium means the polarization of the medium due to the applied electric field has nothing to do with the strength of the electric field. 就说你的那个介质的特性本身跟电场的强度没有关系就是它始终都会达到这个 polarization 跟电场成正比那如果是非线性光学的情况，我们就会讨论的就会是稍微不同So if we discuss nonlinear optics, then we encounter the situation that the property of the medium may be influenced by the strength of the electric field. However, up to now we consider only the linear medium, which means although it's possible that polarization and the electric field may along different directions, but they are always proportional to each other. So this means the relation between the electric field and the electric polarization is linear. Okay. 好，我们在下一堂课会再来仔细讲这个内容，在这边跟下课讲。 Suppose we consider two specific directions that the P vector is proportional to the applied E vector, E field. Okay. Say this direction is X and this direction is Y. When I apply electric field along the X direction, we have Px equal to epsilon 0 chi x times Ex. And we have P. If I apply the electric field along the Y direction, we have Py equal to epsilon 0 times chi y Ey. And here we assume chi x and chi y are different. Okay, so if I apply an electric field along an arbitrary direction, and I can treat this E vector as the superposition of two components, one along the X direction, the other along the Y direction. And since the coefficient chi x and chi y are different, this means that Py over Px is equal to chi y over chi x times Ey over Ex. So this means that the ratio between Py and the Px is different from the ratio between Ey and Ex. This difference means that we, in general, has a P vector along a different direction. Okay. This means that, in general, P vector is not parallel to the E vector. Okay, for this anisotropic medium. For isotropic medium, we have no such problem because for isotropic medium, we have a common chi factor here. Okay, so you will always get the P vector along the same direction as the E vector. Okay. So this also implies that when we consider the D vector displacement field, D vector is the sum of epsilon 0 E plus P. So D vector is also, in general, it is also not parallel to the direction of the E vector. So if we want to describe this situation and we assume the medium to be a linear medium, then we can generalize the concept of chi and epsilon from number to so-called tensor. This means that now the relation between P and E is described as this chi 1, 1, chi 1, 2, chi 1, 3, chi 2, 1, chi 2, 2, chi 2, 3, chi 3, 1, chi 3, 2, chi 3, 2 times Ex, Ey, and 的意思。对。You can also write this as P1, P2, P3, E1, E2, E3. 1, 2, 3 represent X, Y, Z. Similar to this, we can write the relation between D and E as epsilon 1, 1, epsilon 1, 2, epsilon 1, 3, 2, 1, 2, 2, 2, 3。用的不是这一种写法，它是写成这样啊。就 epsilon 有两种写法。如果去看这个，同学如果有用过这个 latex 啊，或者有稍微写过一点希腊字母，就会知道说，这个 epsilon 有两种写法。就用课本的写法。Okay. So in general, the relation between D and E or P and E are described by this matrix relation, the linear relation. Okay. So since you have already learned about linear algebra, you know that for a square matrix, you can find its eigenvalue and eigenvector. Okay. Once we find eigenvalue and eigenvector, this means that we find a proper coordinate system. In that proper coordinate system, the epsilon behaves like a diagonal matrix. OK， 事实上，一般来说啊，我们的这个材料呢，如果你没有考虑很严重的吸收的话啊，如果这个材料不是一个 loss 很大的材料啊，一般吸收如果可以忽略的话，其实仔细分析会发现这个 epsilon 有以下的特性啊。So in general, if the medium is not a very lossy medium, which means it does not absorb electromagnetic energy dramatically, then usually we can find that the epsilon matrix has this property. Epsilon ij is equal to epsilon ji star. This means that the epsilon matrix is equal to the epsilon matrix dagger. We have already introduced the concept of Hermitian conjugate. Okay, Hermitian conjugate means take the transpose and do the complex conjugate. Transpose means exchange the two indexes of the elements, and the complex conjugate is notation star. Okay, so if epsilon is equal to epsilon star, then this matrix is called Hermitian matrix. Hermitian matrix has a very beautiful property that its eigenvalue is its eigenvalues are real and its eigenvectors are orthogonal to each other. Okay. Hermitian matrix means all the eigenvalues values of epsilon are real. And the eigenvectors are orthogonal to each other.就你随便抓两个 eigenvector， 它是正交，然后它的 eigenvalue 呢都是实数。好，这是 Hermitian matrix 的特色。好 ，Hermitian matrix 特色。那这个特色有什么用处呢？现在的用处就是，我们后续我们其实就会直接把我们的坐标系转到那个 eigenvector 的方向。啊，就是它的3个坐标轴就转到 eigenvector 的方向。因为你现在 eigenvector 两两正交嘛，那你 3 by 3的 matrix 会有3个 eigenvector， 那每两个都两两正交，所以它可以构成一个正交坐标系，所以我们就可以把这个坐标轴就转到那个坐标系去，跟它一致。那跟它一致的时候会变成怎样呢？这个矩阵就会变成 diagonal form， 是相当于是已经把它对角化了啊。So this relation, you know that when we change coordinate system, we will change the 3 components of the E vector. We also will change the 3 components of E vector. And in the same time, the whole matrix elements will be changed according to certain rule. What is the rule? I can show you the rule. Suppose originally I have a coordinate system. In that system, I can write the d vector as dx, dy, dz, and the e vector as dx, dy, dz. And there is the relation d equal to epsilon times e. Here d is a column vector, e is a column vector, and epsilon is a square matrix. Now I change coordinate system from x, y, z to x prime, y prime, z prime. Then I can write the new components of d as d prime. D prime is dx prime, dy prime, dz prime. Okay, and e prime is ex prime, ey prime, and ez prime. Okay. The d and the d prime, or e and e prime, are related by this relation. Here R is the rotation matrix. R is the rotation matrix between the 2 coordinate systems. Rotation matrix between x, y, z, and x prime, y prime, z prime. We use the matrix R to rotate our coordinate system from x, y, z to x prime, y prime, z prime. Now we see that we have this relation between d and e. D is epsilon times e. So if I multiply our matrix to d, I get R epsilon, R inverse times R e. Okay. Here, R inverse R is equal to unit matrix, identity matrix. So the result do nothing to E. And the left hand side we have this R matrix. Now we know that RD is equal to B prime. And RE is equal to E prime. Okay. And we have this relation. So what is R epsilon R inverse? This is nothing but epsilon prime. Okay. So we keep the form of this relation. We have the relation between D and E through epsilon. Then when we change our coordinate system from xyz to x prime, y prime, z prime, then the relation between D prime and E prime is through this epsilon prime matrix. Okay, so we see that epsilon prime is related to epsilon by this transformation. This is a so-called similarity transformation.相似变换啊，相似变换，相似变换其实就是我们用来对角化一个矩阵左右的方法，啊，就是你基本上呢，就是你经由一个相似变换，你可以把一个矩阵对角化。那我们在第3章时候不是有透过一个旋转的，让我们的这个描述那个椭圆的那个矩阵对角化，啊，那这边其实也是在做同样的事，只是变成3维的，啊，3维的，啊 ，similarity transformation。那我们通常称呼这样的东西，这个 epsilon 呢，我们通常并不会叫它 matrix， 而会叫它 tensor。epsilon is a tensor。虽然它的表达是一个 matrix。但是我普通的 matrix 不会随便改变，就是写下来是什么就是什么啊。但这边的这个 matrix 呢，它是会随坐标选择不同而改变。那而且是一种有规范的改变啊。这一种东西，这种写下来是一个矩阵，但是它会随坐标以固定的规律改变的这种东西，我们叫它一个 tensor 啊。所以你可以把它看成是。Vector 观念的一个推广啊， so originally we have scalar. Scalar is invariant under coordinate transformation. Then we have vector. Vector changes components according to certain rule. When we change our coordinate system from x, y, z to x prime, y prime, z prime. Okay. The rule is that we multiply the matrix R to the original vector. We get a new expression of this vector, okay? And how about the so-called tensor? In fact, this is a so-called rank 2 tensor. For this rank 2 tensor, the transformation rule is this, okay? R epsilon R inverse. The R represents the coordinate transformation, the rotation, okay? So through this transformation, if we choose a proper rotation, we choose a rotation appropriately, then we can make this epsilon matrix diagonal. Okay? This means that we have already found the so-called principal axis. Principal axis means you can treat principal axis as the eigenvectors. Okay. Eigenvector as epsilon. We change our coordinate to so-called principal axis system. In principal axis system, we have epsilon written as epsilon x 0, 0, epsilon y 0, epsilon z 0. Okay. We change our coordinate system. So finally, we have the 3 coordinate axes along the 3 eigenvectors of this tensor epsilon. Then, in this new coordinate system, the epsilon tensor becomes diagonal matrix. These 3 elements in this diagonal matrix are in fact the 3 eigenvalues of this epsilon matrix. 好，这3个对角分量其实就是它的 eigenvalue。好，那我们在这些相似变换里面，你无论怎么变，这个矩阵的 eigenvalue 其实是不会变的。相似变换并不会改变 eigenvalue。好，所以那3个 eigenvalue 是固定的。好，然后呢，相似变换也不会真正改变 eigenvector 啊，只是你 eigenvector 在星座坐标的分量表达会不一样，但其实就是去可以找到它的 eigenvector 啊。So, hereafter, we will always work in the so-called principal axis system. So everything becomes simpler than the original arbitrary coordinate system representation. 就是说，我们跑到了这个所谓的主轴坐标的时候，一切就变简单，一切就变简单。然后呢，这个联系 E 和 D 的这个东西，就是一个所谓的 tensor。那 tensor 其实在日常生活中有一些其他的例子我昨天常举的一个例子是，就大家如果学过这个谱物的时候，你们学过一个东西叫转动惯量，moment of inertia。转动惯量在谱物阶段没有去强调它是一个 tensor 因为呢，都会选择特殊的轴呢去表达它。可是 in general 它其实是一个 tensor。就是你如果有学过物理系的所谓钢体动力学一部分的话，你会知道说其实它是一个 tensor， 它是一个 tensor。那所以你要找到一个主轴，让它对角化，才会让一切好算，才会让一切好算。那我们现在呢，就来进入到这个完全在主轴里面去讨论的情况。So now we adopt this principal axis system and discuss everything. We now want to find the propagation behavior of the electromagnetic wave in anisotropic medium. Okay, and we choose our coordinate system to be the principal axis system. So suppose we can write our E vector of the electromagnetic wave as ERT. We write ERT as E times exponential I omega t minus k dot r. And the corresponding H vector, HRT, we write HRT as H exponential I omega t minus k dot r. Here, in general, E and H are complex vectors. Here we do not care about its taking the real part of something. We just use the complex representation of the E and H vector. So here, E and H are both complex in general. And here, the notation E and H represent constant complex vectors. All the coordinate and space dependence are written in this phase vector. OK， 就是在这 phase vector 里面包含了它所有的这个跟时间跟空间有关的一些变化。那剩下这些呢？都是常数项类就是说跟时间、空间没有关系，这就代表 E 和 H 就是它们各自的 polarization 就是电场的 polarization vector 跟 H 的 polarization vector。So now we use the Maxwell equations to study the behavior of the electromagnetic wave. We know that these two equations are most important. The first is the Faraday induction law, which can be written as minus mu partial T partial H. And Ampere's law. Without current density. So we have learned in chapter 1 that we can replace del by minus ik if we consider the plane wave of this form. And we can replace the time derivative by I omega. So this equation tells us that minus ik cross E is equal to minus I omega mu times H. So this means that K cross E is equal to omega mu times H. Okay. Similarly, for the Ampere's law, minus ik cross H is equal to I omega epsilon times E. Remember now that epsilon is a matrix, not a number. This is a matrix in the principal coordinate system. Okay. So this implies that K cross H is equal to minus omega epsilon times E. So now we have this two equation. K cross E is equal to omega mu H, and the K cross H is equal to minus omega epsilon E. So now if I substitute, if I take, we do the operation K cross E, I get omega mu K cross H. Okay. Remember that now mu is a number, okay, not a matrix. Okay. We assume only epsilon is a matrix and the mu is a number. Okay. Then since K cross H is equal to minus omega epsilon, we now have minus omega squared mu epsilon times E. Okay. 抱歉，我这边可能需要先暂停5分钟，因为我有写想去上厕所啊。那我几分钟后。 Okay, let me continue this process. There is a formula about this this kind of operation in vector analysis. When we encounter A cross B cross C, there is a formula A dot C times B minus A dot B times C. Okay. If you are not familiar with this formula, you can check the chapter 1 of some electrodynamics book or the final page inside the cover. Okay. So the left hand side gives us K dot E times K minus K dot K, which is equal to K squared times E, is equal to omega squared mu epsilon times E. Okay? So if we write the component one by one, say if we try to write down the x component of this equation, we have K dot E times Kx minus K squared times Ex equal to omega squared mu times, here epsilon times E is nothing but D, dx. Now we know that we have chosen the coordinate system to be of diagonal form. Epsilon is diagonal form. For diagonal form, epsilon, epsilon x, epsilon y, epsilon z. When it times Ex, Ey, and Ez, it gives us this epsilon x Ex, epsilon y Ey, epsilon z Ez. Okay, so the x component now is equal to epsilon x times Ex. And we can rewrite this as Kx Ex plus Ky Ey plus Kz Ez times Kx minus K squared Ex is equal to sorry, here we have a minus sign. We have a minus sign here. Minus sign. Okay. So minus square mu epsilon x dx. Okay. So I can write this as I can write this as omega squared mu epsilon x minus k squared plus kx squared times ex plus ky times ey plus kc times ec equal to 0. Okay. So similarly, we can write down the y component and the z component. The y component z x z y So finally, we have this. The equation in the textbook 4.2-8. So now we have this relation. What's the use of this relation? This relation is used to derive the so-called dispersion relation between omega and k. 色散关系就是要找出 omega 跟 k 之间的函数关系。那在 isotropic 介质，这个函数关系不需要用到这么复杂的方式去得到，但是呢，我们现在是 anisotropic 介质，所以就会复杂一点。So you see, now we have some kind of matrix multiplied to the E vector equal to 0. So if this matrix has inverse matrix, then we can multiply the inverse matrix from left-hand side to it to cancel this matrix, and then we will conclude that E equal to 0, which means the electric field is nothing. Okay. However, we are not. We consider the situation that there is the electric field. Okay. So this implies that this matrix cannot have inverse matrix. Okay. Cannot have inverse. We know that there is a formula to write down the inverse matrix of matrix by some kind of formula. If you note the formula, you will see that in the formula there is a denominator equal to the determinant of the matrix. Okay, so this means that if the determinant of the matrix is not equal to 0, you can always define the inverse matrix. So you can multiply the inverse matrix to it and cancel this and get the conclusion that E is equal to 0. So if we want E not equal to 0, then this means that the determinant of the matrix must be equal to 0. So it has no inverse matrix. Okay. So this means that the determinant of this matrix is equal to 0. And this condition gives us the dispersion relation, which means the relation between the k vector and the omega. So now we try to derive the dispersion relation from the condition that the determinant of this matrix equal to 0. To simplify our derivation, I define three quantities. I define AX as omega squared mu epsilon x minus k squared. Define AY as omega squared mu epsilon y minus k squared, and I define AC equal to omega squared mu epsilon z minus k squared. This three quantity has nothing to do with any vector. It's just three different reference quantities. Okay. Then I can write this as AX plus KX squared, okay, and KX, KY, KX, KC. AY plus KY squared, AC plus KC squared, KX, KY, KX, KC, KY, KC, KY, KC. The determinant of this is equal to 0. Okay. There is no simple way to calculate this determinant, so I just use the brute force， 就直接爆开直接爆开就是不用任何的技巧。我大概再讲5分钟，因为我刚才去上厕所上5分钟，我再讲5分钟So first we have AX plus KX squared times AY plus KY squared times AC plus KC squared. Okay, and then we have two same result 2 KX squared, KY squared, v squared. Okay, and then 另外三个呢是只有 a 的一次方啊 ，minus ax plus kx squared times ky squared kz squared minus ay plus ky squared times kx squared times kz squared minus ac plus kz squared times kx squared ky squared equal to 0. Okay. So this means we have ax, ay, ac 这三个乘在一起，然后呢，两个乘在一起再乘第三个ax, ay, kz squared plus ay, ac, kx squared plus ac, ax, ky squared 这是三个 a 的，两个 a 的，还有一个 a 的一个 a 的是 ax, ky squared, kz squared plus ay, kx squared, kz squared plus ac, kx squared, ky squared 然后没有 a 的三个乘在一起，再加它变3 3 Okay, and then minus ax, ky squared, kz squared minus ay, kz squared, kx squared minus ac, kx squared, ky squared and minus 1, 2, 3, 3 kx squared, ky squared, kz squared equal to 0. So we see that here this cancel with this, okay, and this cancel with this, and this cancel with this, and this cancel with this. Okay. So finally we have this result. Ax, ay, ac plus ax, ay, kz squared plus ay, ac, kx squared plus ac, ax, ky squared. Just like that. So these are the results. 那我们下一堂课再来研究这究竟是什么。所以我们这边先下课。So now we have this relation. And what does it mean? First, we know that ax is equal to omega squared mu epsilon x minus k squared. And now we define three quantities we define nx squared as epsilon x over epsilon naught, ny squared define ny squared as epsilon y over epsilon naught, nz squared is defined as epsilon z over epsilon naught. These three quantities are three reference refractive indices. Its meaning will become clear afterward. Okay? Here you just treat them as some reference refractive indices. And K vector, we learned in chapter 1 that K vector is omega over c times n times the unit vector along the propagation direction. In isotropic medium, the refractive index n is a fixed quantity. It's a orientation independent quantity. Okay. However, now we discuss this anisotropic medium. I will show you that the refractive index n is a function of direction. You change propagation direction, then usually you change the refractive index. It is a variable that we need to solve. Okay， 就我们必须是一个这个东西是一个 unknown 啊 ，this quantity, the refractive index in anisotropic medium is an unknown. We need to solve for it. Okay. In isotropic medium, we do not need to do this because the refractive index is given. Okay. Now we need to solve for it. Okay. How to do this? We now have this can be written as this means that epsilon x is nothing but nx squared times epsilon naught. Okay, so this is equal to omega squared mu epsilon naught times nx squared minus omega squared over c squared times n squared. Here n is an unknown. Okay, so this means that here this is equal to. Remember that in optical material, we always treat mu as mu naught. Then mu naught times epsilon naught is nothing but 1 over c squared. So this becomes omega squared over c squared times nx squared minus n squared. Okay. Here, nx squared is a known quantity because we know, if we know epsilon x, then we know nx squared. Okay. So this is equal to omega squared over c squared times nx squared minus n squared. And similarly, ay is omega squared over c squared times ny squared minus n squared. And finally, ac is omega squared over c squared times nz squared minus n squared. Okay. So what is this? What does this equation mean? So you see kx squared. What does kx squared mean? Kx is omega over c times n times sx. Here sx is the x component of the s vector. S vector is a unit vector along the propagation direction. So kx squared is omega squared over c squared times n squared times sx squared. Okay, and the ky squared is omega squared over c squared n squared sy squared, and the kz squared is omega squared over c squared times n squared times sz squared. Okay. So finally, we have this. Here we have 3 terms. So we have a factor omega over c to the 6th power times n x squared minus n squared, ny squared minus n squared, and nz squared minus n squared. Okay. Here ax, ay, both ax, ay provide omega over c squared, and kz also have this omega over c squared. So we still have omega over c to the 6th power. Okay, and nx squared minus n squared times ny squared minus n squared times n squared sz squared. Plus ny squared minus n squared, nz squared minus n squared s x squared. Okay, and the plus nz squared minus n squared nx squared minus n squared times n squared times s y squared equal to 0. So we see that this omega over c to the 6th power is the common factor. We can drop them. And if you divide the whole equation by n squared times this 3 bracket, okay, nx squared minus n squared, ny squared minus n squared, nz squared minus n squared. We divide the whole equation by this. Then we find here find this 1 over n squared plus sx squared over nx squared minus n squared plus sy squared ny squared minus n squared plus sz squared nz squared minus n squared equal to 0. Okay. We can rewrite this as this. And this equation has a name. The name is Fresnel's equation of wave normal. This is the equation in the textbook 4.2-10. 4.2-10. Okay. 好，这个是我们等一下呢还会看到说，我们从这里啊要怎么去解这个refracting index 啊。So we can solve for the refracting index from this equation. How can we do this? We noted that here S is the S vector is a unit vector. S vector is a unit vector. This means that S dot S is equal to 1, and this is equal to Sx squared plus sy squared plus sd squared. Okay. So this means that if you multiply the whole equation by n squared and substitute this 1 with the summation of the 3 s squared terms, then we see that n squared sx squared over n squared minus nx squared, okay, minus sx squared plus n squared sy squared over n squared minus ny squared minus sy squared plus n squared sd squared over n squared minus nz squared minus sd squared is equal to 0. Okay, and this is nothing but this equation. So we get this equation. This equation is equivalent to the original equation. Okay. Then, so sometimes it is more convenient to use this equation to derive something. So first, I want to show you that we can derive the reflecting index from this equation. We have this nx squared as x squared over n squared minus nx squared plus ny squared as y squared n squared minus ny squared plus nz squared as z squared over n squared minus nz squared equals 0. So now I try to multiply the whole equation by this factor. Multiply this factor to the whole equation. Then we get plus okay. So this equation now becomes this equation. Simple observation tells you that the equation is the fourth power equation, which has the form a n to the fifth power plus b n squared plus c equal to 0. In fact, I can write down the three coefficients. Here what is the coefficient A? A is nx squared sx squared plus ny squared sy squared plus nz squared sz squared. Okay. This is the coefficient A. And what is coefficient B? B is coefficient B is the coefficient of n squared. So we have this minus ny squared plus nz squared times nx squared sx squared, and minus nz squared plus nx squared times ny squared sy squared minus nx squared plus ny squared times nz squared sc squared. And what is C? see we have nx squared, ny squared, nz squared times sx squared plus sy squared plus sd squared. And the sum of these three squared gives you 1. So finally c is equal to nx squared, ny squared, nz squared. And this is a positive quantity. This is a positive quantity, and this is a negative quantity. So from this equation, we know that we can solve n squared. N squared is equal to here we know that since b is negative, so minus b is positive. So this gives us two positive numbers, okay? And we can take the square root of them. We get two solution of the refractive indices. 就说我们在普通 isotropic 介词里面的时候 ，refractive index 折射率呢是给定的。可是，在 anisotropic 介词里面呢，折射率跟你传播的方向有关。好，那传播方向的资讯就藏在这个 sx、sy、sg。然后呢，还有3个参考的折射率是这个 nx、ny 的。那你利用这些呢，可以写下这个系数 a、b、c。然后根据这 a、b、c 呢写下来之后，你就可以去对一个给定的方向解出它的2个折射率。所以一个传播方向会对应到2个折射率。那什么情况会一个传播方向对应2个折射率呢？答案是这2个不同折射率它的偏正不一样，它的correlation。So for these two different refracting indices, the corresponding polarization are different. Different. 好，那我们要怎么去找到这个 polarization？ 我们现在来提供一个方法。So now I discuss how to find the corresponding polarization of the electric field. Okay. Once again, we start our discussion from these two equations. K cross E is equal to omega mu h, and the K cross h is equal to minus omega epsilon E. So we use these two equations to find the corresponding polarization of the E vector. I still use the same strategy. K cross is equal to omega mu K cross H. And this is equal to minus omega squared mu epsilon. And just like before, we know the result is K dot E times K minus K squared times E is equal to minus omega squared mu epsilon E. Now I write this equation as this. I move this term to the right side. Sorry. So, if we try to find the component one by one, we have K dot E times K squared equal to K squared minus omega mu epsilon x times dx. Okay. For dx, the epsilon behave like epsilon x. And for the y component, we replace epsilon x by epsilon y. And for the c component, we have these three relations. And usually, in general, K squared is not equal to this term, not equal to this term, not equal to this term. Okay. So this means that we can divide every equation by the corresponding this kind of term. So we can get that dx is kx over k squared minus omega mu epsilon x times k dot E. And dy is ky over k squared minus omega squared mu epsilon y times k squared. And dc kc over k squared minus omega squared mu epsilon times k. Here I must emphasize that in anisotropic medium, in general, K dot E is not equal to 0. Okay, because According to Maxwell equation, we have divergence D equal to rho f. If rho f is equal to 0, what we can obtain is k dot D equal to 0. This means that suppose this is the direction k, and then the direction D is perpendicular to k. However, as I have already explained before, for an arbitrary propagation direction, in general, E vector and D vector are not parallel to each other. So, in general, k dot E is not equal to 0. Okay? So, this k dot E in general is not equal to 0. Then you observe that the so-called k dot E is nothing but kx times ex plus ky times dy plus kz times ec. Here we have ex, ey, and ec. I can time this to, I can multiply kx to this term, ky to this term, and kz to this term, and sum them over to get k dot E. Then I can drop the common factor k dot E to get the equation equivalent to the Fresnel's equation of Rayleigh. OK， 就是说我刚刚用矩阵很复杂的方式推导那个方程式，现在其实可以很简单得到，就是我把这边乘上 k， 这边乘上 ky， 这边乘上 kz 加起来，我就会凑出 k dot E 来。然后两边都有 k dot E， 我把 k dot E 拿掉，剩下的那三个加起来的东西，得到就是刚刚的Fresnel's equation。OK， 好，那现在除了这个之外，这里还有另外一个用处，就是这里告诉你的是什么？就是说，如果你觉得 k dot E 并不是0，那这表示什么呢？ This means that now ex, ey, ec is k dot E times this. Since in general k dot E is not equal to 0, so we get the result that the E vector is proportional to this. Okay. So you can use this to represent the correlation of the E vector. This is just the result listed in the textbook. Okay. And I can further simplify the expression by this. We know that Kj is omega over c n times Sj. J takes 1, 2, 3 to represent x, y, z. So this is proportional to this. Since all three components has the same factor n and omega over c, so we can ignore them and write It's like Sx n squared minus nx squared. Okay? And Sy over n squared minus ny squared. And Sz over n squared minus nz squared. Okay? This is also the expression of the quantization of the E vector 4.2-11 in the textbook. Okay. 好，这个是关于 quantization 啊，关于 quantization， 就是说，你如果刚刚不是用那个方向，你去给出一个方程式，然后你可以写出两个 n 嘛。你带第一个 n 进去，你就会得到第一个 quantization； 你带第二个 n 进去，就得到第二个 quantization。啊 So we have this equation. We can solve the n from using this equation. We get n1, n2. If we substitute n1 to this equation, we get the E vector quantization for the first propagating mode. And if I substitute n2 to this expression, I get the quantization of the E vector for the second propagating mode. Okay, 好，就是你把对应的 n 带进去，就得到对应的 quantization。那另外还有一个刚刚没有特别花时间讲，现在讲一下，就是关于这个 D vector、E vector 跟 H vector 的方向关系啊。We know that K cross E is equal to omega mu H, and K cross H is minus omega B. Epsilon E is just B. So according to this equation, suppose this is the direction of the K vector. Okay. We know that K dot B is equal to 0. And K dot B is mu K dot H is equal to 0. So this means that B is orthogonal to K. The H is also orthogonal to K. Okay. B is orthogonal to K, and the H is also orthogonal to K. And this equation further tells you that D vector is perpendicular to H vector. Okay. Here we only know D vector perpendicular to K and H vector perpendicular to K, but we do not know the relation between E and H. They can be have angle different from half pi between them. However, this equation tells us that K cross H minus sign along this direction. So this B is perpendicular to H also. 所以这边就是这些都是垂直。And we know that K cross E is proportional to H, which means that what is the direction of E? We know that in general E is not parallel to D. So this means that E is located in the KD plane. E is in the KD plane. 电场在哪个地？虽然电场跟第一场不见得同方向，但我们可以知道电场落在哪个平面上？它落在 KD 平面上 ，KD 平面上。因为你 K cross E 的方向是 H 的方向，表示什么呢 ？H 既垂直于 K 又垂直于 E， 那所以 E 不可能是有 H 方向的分量，所以 E 一定落在 KD 平面上，但是又因为 D 和 E 一般来讲并不平行，所以我们就只能说 E 落在 KD 平面上，所以它们之间的这个方向关系大概是这样子。那你可以把它想成 K 和 D 是那个黑板，然后呢 H 就指出黑板，那 E 是落在黑板上，但是没有平行于 D， 所以大概是这样的情况。You can treat the KD plane as the blackboard. Then E is on this blackboard. D, K are also on the blackboard, but H is pointing outside this blackboard. 好，这是关于它们的这个方向上的关系。然后另外呢，还有就是。这边有个图我需要解释一下，就是我们刚刚不是一个传播方向会对应到两个 n 吗？那这两个 n 要拿来干嘛？答案就是呢，我们现在的这个所谓 dispersion ratio 是一个双层的体重。Kx, Kz, Ky. Suppose the three reference refract index nx, ny, nz has this order. Okay, nx is smaller than ny is smaller than nz. Okay. Then if we plot the relation between omega and k, we have this relation. This relation can be rewritten as relation of omega of k. Then for a given omega, given frequency, if you plot all the possible k vector, then it forms a double shell structure. 边就是ny omega over c 是 nz omega over c， 然后是nx omega over c。by omega plus
个关系是，你把它重新改回用欧米伽跟 k 去写，然后你给定一个欧米伽的时候，你把所有的 k 的集合，好，就同一个欧米伽的不同的 k 的集合画出来，你会得到一个有点丑的曲面，好，那个曲面是双层的，好，双层的曲面，好，那这双层曲面呢会从里面穿出外面来，然后从外面又跑进里面去，然后在这个曲面呢跟这三个坐标面，好 k ky ky k k z k x 的交叉呢，会是一个椭圆跟一个圆，好，就每一个平面跟这个双层曲面的这个交集都是一个椭圆一个圆一个椭圆，只是呢这个你并不能够把它想成是一个椭球加一颗球，不是，只有在很特殊的情况上，在所谓的 uniaxial crystal 的时候是那样，但是呢，如果不是 uniaxial crystal 的时候呢，它是一个有点丑的曲面啊。So if you plot all the possible k points corresponding to the same omega frequency, then you get an ugly double shell surface. Okay, this double shell surface has the property that if you consider the intersection of the double shell surface with the three possible coordinate plan, which means the kx, ky, kz, and the kz, kx plan, then you find the three corresponding intersection between the surface and the plan gives you one ellipse, one circle. Okay, 就每一个面上它都会是一个椭圆跟一个圆，但是它不是一个椭球加一颗球在上面啊。In 3D, the surface is not the collection of one sphere with one ellipsoid. Okay. However, the intersection of the surface with the three coordinate plan, for every one, you get one ellipse and one circle. 我们在下一次会再仔细把这些内容讲清楚。好，那我们今天就先到这里。